I don't know if I'm spelling correctly. Is that a reasonable word to use for matching? Yeah. Is what there's a graph in which every vertex has degree 1. Oh, I'm supposed to say that every vertex has degree at most 1. Every vertex has at most 1 neighbor. So something that looks like this. There may be some vertices left over. And it's a perfect matching, has no vertices left over. Okay? So, there's questions like, when does our graph contain a matching?
I have a question about values. He used a result about chains and anti-chains. That says if you have a lot of chains, you must have one of
Yeah.
those. Does that come directly from the result you studied already?
No, so that was, I was just talking to Baylor and he asked me if I was going to prove it. And I said no, and he said, no, you must prove it, of course. So, but actually the proof is not very difficult. So I think perhaps might be worth leaving as an example. Maybe I'll put it on the second Lister. So what does the Dilworth's theorem say? It says, so given a post set, a partially ordered set, with n vertices. So what's a partially ordered set? So does everyone know or not? Who does not know the definition of a partially ordered set? Okay, so I'll tell you. So completely reasonable not to know. So so there's a partial order on the set. So some of the elements are less than others. And it has to satisfy sort of the obvious things that you'd expect. If A is less than B and B is less than C, then A is less than C. And what else? That's it, right? You can't be less than, you can't have, this implies that B is not less than A. You can't have both of them. Like yeah. But not all elements have to be ordered. So you can have incomparable elements. Yeah, okay, so there exists either a chain of size k, or an anti-chain of size n over k. So what's a chain? A chain is a sequence of comparable elements. Right? So this one's greater than that one, is greater than that one, is greater than that one. An anti-chain is a collection of incomparable elements. So none of them are greater than the other. Right? So I called, when we did Sperner's theorem, I called something anti-chain. So why? Because if you look at all of the subsets of 1 up to n, you can think of them as being a partially ordered set, with the partial order given by inclusion. Right? So you put a partial order on sets by saying that A is less than B if A is contained in B. Right? Right, so there are some comparable elements of different sizes, some incomparable elements. Does it make sense? So this is an example, the power set of 1 up to n is an example of a post set. And so what do you really do here? So it really says you can sort of partition into chains, right?
So that's true for
Yeah, so for all k, for all k. So either one or the other one. So you get the largest chain, then you must have an anti-chain of size. Right, of size, whatever. This is proved in 1950 or something, and the proof is very short, so I think it can be an exercise.
When you write n over k, like in general, does it?
Would it have been floor and ceiling?
Is it always 4 or?
Yeah, so it's not always floor. So I normally don't put floors and ceilings in when they don't matter. Sometimes they do matter. So perhaps this would be false if you put the wrong one. So I mean, there's some interpretation of this which is correct, and you should work out what it is. So I think here actually it means, I think you can really do either this or this. So perhaps I'll give you a heuristic proof of this without checking the details. So let's just take a maximal chain, pull it out, take another maximal chain. So if we do a maximal chain, what do I claim? Do I claim that every... Do I mean this or not? I want to partition into chains such that they're all of size at most k, and then take an anti-chain that's basically one element of each. So I think maybe I'm even something slightly stronger is true. The floors and ceilings are in my favor. I can add one or something. Yeah, so something like this. Yeah, I'll put it on the second lista maybe, and then we can discuss it after you've thought about it properly. Right. More questions about anything? No? Okay. So general question. So when must G contain a perfect matching? Right, what conditions on G guarantee that you contain a perfect matching? So one obvious condition is n needs to be even. Right? Okay. In fact, this question is it's a bit nicer and a bit simpler, and actually perhaps even more useful if we think not about graphs in general, but if we restrict the graph being bipartite. So let's restrict to a bipartite graph with vertex at A union B, where A equals B equals n. Okay? So this is a rare case when our graph does not have n vertices, because it has 2n vertices. Okay? Just to make sure it's even. But also bipartite makes life a bit simpler. Okay. So who can give me... So I said the first one, and it's even. Who can give me another necessary condition? It doesn't need to be connected, right? Because if the graph could just be this, right? That's a perfect matching, but it's not connected. Yeah, so connectivity is stronger than having a matching, perfect matching. But what condition do you need? Like a really simple condition. Yeah. Oh, sorry. Yeah, right. So every vertex must have at least one neighbor. That's a sufficient, sorry, I mean a necessary condition, right? Not sufficient, I must have necessary conditions. So this implies that the degree of V is at least 1 for every vertex. Okay, that's a really simple condition. Is it sufficient? No. Counterexample. Do I need 3? I probably need 3 vertices, do I? Okay. So, okay, we're not sufficient yet, so let's have more necessary conditions. What's another necessary condition? And preferably one which is not satisfied by this graph. Right, you can see this as no perfect matching? Right, all the edges have to touch either this vertex or this vertex. You need 3 edges, so you can't. So why does this not have a matching? What's a condition this fails? Right. So here are 2 vertices on the left. Now I'm talking nonsense. Here are 2 vertices on the left. And their neighborhoods, they both have a neighbor, but it's the same neighbor. Right? And this guy can't have an edge to both of them in the matching. So another condition that we have is that for all u and v in A, the size of the neighborhood of u union the neighborhood of v, this, is at least 2. Right? U not equal to v. Right? If you have u and v, and they have only one neighbor, it's the same one, then you're not going to find a matching. You're looking as if, I can't tell from your faces. This is completely obvious or completely confusing? Completely obvious. So what's the general condition? How many of you already know this theorem, by the way? Okay, not many of you. Okay, someone else. Somebody who doesn't know the theorem. To generalize this, what's the condition? Yeah, exactly. In fact, for every subset of A, the size of the neighborhood. So I'm going to write neighborhood of S to be the size of the union of the neighborhoods. If you have size at least S. Right? So Hall's theorem says this is all you need. Right? So this obviously necessary condition is sufficient. So let's try and prove it. So let's let G be a bipartite graph, parts both sides n. Then the size of n of S is at least S for all S in A, if and only if G has a perfect matching. Okay? And this way, we just checked. So this way is obvious. Let's do this way. It's okay? Statement's clear? Yeah. So it's an incredibly simple characterization of graphs, bipartite graphs with perfect matching. Okay, so how do you want to prove the other direction? So given a graph with this property, this is called the Hall's condition. We're going to show that it has a perfect matching.
Will you try finding a set which its neighborhood divided by the size of itself is minimum, and then try matching there?
Aha. Yes, this sounds like a non-crazy idea. So here's an idea. So pick some subset with this ratio minimal. Then here's S. Here's the neighborhood of S. Here's the rest. I should make this in the same size, sorry. Okay, can anyone expand on this idea? It's a good idea, but let's...
I think this is not going to work because the minimum will be the whole set.
Right, so for the whole set, this ratio will be 1. So we take it arbitrarily as minimal, and you know it was at least 1. So yes, that will be an example of the whole set, and then in the same position you started with. Okay, but this is still a good idea. Let's try and pick a clever set S. So what's our proof strategy? What's a sensible proof strategy? Okay, so here's a good idea. This is another good idea. So it's a different version of this idea. So if there's a vertex of degree 1, why are we done? Yeah, exactly. If there's a vertex degree 1, it has to match this guy. And then you've got n-1 vertices here and n-1 vertices here. And hopefully we've got a matching here. So why do we have matching here? Induction. And why does Hall's conditions, why does it hold here? So this is G prime, let's say. So take out, so G prime, take out U, take out V, its neighbor V. So okay, so G prime is G minus U minus V. There's another example when you're supposed to understand the notation from the context, right? So here I'm just meaning remove both vertices. Right, so the claim is that the neighborhood in G prime of S is at least size of S for all S in A minus U. Proof.
If you pick any S and then unite it with the vertex 2, we know that it must satisfy the ALON condition.
So neighborhood in G of S union U is at least S plus 1 by Hall, by assumption. And the neighborhood in G prime of S, how does that relate to this? Yeah, this guy doesn't necessarily have degree 1, right? This could be connected to everybody. Right? But it's at least this thing minus 1. Right? Because you've only lost V. So this thing is at least S. OK, so that was a proof in the case there exists a vertex of degree 1. Now let's turn that into a proof in general. Who can take this proof and turn it into an actual proof of the theorem?
Instead of taking a single vertex, take a subset.
Yeah, take a subset with what property?
Where that's equality.
Aha. Right, so yeah, the nice thing about this thing, this guy, was his neighborhood was exactly size 1, the size of him. So case 1, let's suppose there exists S in A such that the size of the neighborhood equals size of the set.
And it's not equal to
Right. Yes. Otherwise, not going to take us very far.
That's not my idea would work actually. Right, this is a minimal set.
It is a minimal set, but right, but it better have this property.
Yes.
Yeah. Okay, so what do we do in this case? So here's S. Here's the rest. Here's the neighborhood of S. Here's the rest.
I think we can apply induction in this
Right.
because it's proper.
Okay. I think S shouldn't be empty either. Probably. Okay. Right. So, sorry, quickly, just induction, we should check the base case. Base case, I guess, is n equals 1. So this is true as long as there's an edge and the edges are matching. Okay, so that's true for n equals 1. Good. Okay, so inductive hypothesis says, yes, we know the neighborhood of S is exactly this. So we know now that we have to have a matching here and a matching here. Right? We're not going to use any edges that go across. Well, there aren't any edges here. Sorry, there aren't any edges here, and we can't use those because we're already going to have matched here. Right? So, okay, so we know we're doing the right thing by applying induction. We haven't lost anything. Okay, so we want claim. So here's G1 and G2. G1 and G2 satisfy Hall's condition. Proof, I mean, just check, right? So, I shouldn't really call it S, should I? Okay, whatever. So let T be a subset of S implies that the neighborhood in G1 of T is equal to neighbor in G, right? You haven't lost any edges, because there are no edges between here and here. Right? So the size neighborhood of G1 in T is at least T. By whom? That implies the size of this thing is at least T. OK, so that was easy. Well, at G2, so let T be a subset of X, which is A minus S. Right? So the neighborhood in G2 of T is what? Here's T. T has neighbors here, but it also has some neighbors here. So what should we do? It's contained, that's true. But we don't want to lose anything. So what do we do here? Right? We're in exactly this situation here.
We can add this.
Exactly. We add S. So what do we know? That the neighborhood in G, what am I saying? Of S union T is the neighborhood in, what am I doing? Move this over here a little bit. T is opposed to X, right? So know that the neighborhood in G of S union T has size at least S union T by Hall, which equals size of S plus size of T, because T is disjoint from S. Right. Now, how does the thing we actually want compare to that? The neighborhood in G2 of T of S union T. Aha, right. Yeah, sorry. I'm with it. What is this equal to? So, sorry, in G2. What's it sorry, there's no S. Thank you. This guy. Yeah, compared with this, basically. That's what we want to do. Yeah, so let me do the other way around. Let me just say this. The neighborhood in G of S union T equals the neighborhood in G of S, this guy, union the neighborhood in G2 of T. Right? So what does this mean? And this thing has size exactly S. Right? So the size of the neighborhood in G2 of T is at least the size in G of S, neighborhood of S union T minus S. Right? So this thing is at least this thing minus S, which is T. So that proves the claim. So by induction, there's a matching here. And then also, by induction, there's a matching down here. That's the proof. Uh-huh.
I don't know why it's because you lost some edges.
Ah,
The equal.
so, right, so I lost these edges going up, but by adding S in, we know we're not going to use these edges. How do we know that? Because S has to be matched over here. So by adding S, we add in exactly the right amount of the neighborhood, then we can just forget about them because they're already counted here. Right. Yeah, so we lose exactly these guys. That's OK, because they're picked up exactly here. So is it the calculation or the intuition?
The intuition
Is OK. Yeah, so this is being taken care of exactly here. Because, so what's happening? So the neighborhood of this guy down here,
yes, the neighbors of S are the same.
yeah, exactly this. And so that they take care of all the neighbors of here. You don't get anything extra from them. Yeah, exactly. Sorry, case 2. So that's the proof in case 1. How do you prove case 2? I'm going to do case 2 here instead. So the only sets where you get equality are the empty set and everything. So this implies by Hall's condition that n of s is strictly greater than s for all of these things. Yeah, right. We've already, we just have a stronger condition. Right, so we should win by more, but let's just remove, so what do you do in this case? What happens if we just, so I think we could just remove an edge, and then do an induction on the number of edges as well. If we don't want to do an induction on the number of edges, what we can do is just pick a vertex, u, pick a neighbor of u, so u has some neighbors, just pick one, v, and match u to v. And then what happens in the rest? Yeah, so g prime is equal to g minus u minus v again. Right. So claim g prime satisfies Hall's condition.
Seems strange. Because you, for example, if another vertex has only degree 1 and you...
Yeah,
I don't know what to do.
but you do know what to do because we already did it.
Because if you had such brackets,
Then we're in this case. Yeah. So exactly. So the only case you have to worry about, the only time this hurts you, is exactly if you're in the first case. So should I even bother checking it? Here's S. Neighborhood in G prime of S is at least neighborhood in G of S minus 1, which is at least size of S, because this thing is strictly bigger than, right, by the condition. Is it okay? You're looking blankly at me as if I'm cheating. This follows from this. Right? Because they're integers. Okay? Okay. So what do we actually prove? We prove something stronger. Right? In this case, under this condition, we didn't just find a matching. We said for every vertex, for every edge, that edge extends to a matching. Right? The only time when you don't have a choice is if you have a set where it's exactly equal. Right? Okay. So. So a question. Darker, isn't it? When do you get a perfect matching in a random graph? Swinge? How large does P have to be before GMP typically has a perfect matching? So what is the threshold for the existence of a perfect matching in GMP?
Not more bipartite, right?
No more bipartite, yeah. Yeah, so give me some ideas. How would you show that there isn't one, and how would you show that there is one? Yeah, so this is an obvious thing to try, right? If we just proved a theorem about finding matchings, we try and apply it. And perhaps let's try and prove for a lower bound first. So if P is small, then you don't have one. So
I have a question.
Yep.
What is the last law?
Oh, con alta probabilidade with high probability. Is it easy if I write WHP instead? I'm not going to write the whole thing out every time, please. It'd be a disaster. Yeah. Oh. The same meaning it's equally confusing. Yeah, so with probability with probability tending to 1 as n tends to infinity, we'll just think when is it likely? Yeah, it's supposed to be a slightly vague question. Right, so when it doesn't have a what was this? So I mean you can always partition the vertices into two parts, but so what do you mean? Sorry, so it shouldn't. Sorry, so I'm not saying that GMP should be a matching. I'm saying it should contain a matching. So throwing away lots of the edges when you find a matching. So GMP doesn't have to be bipartite. You can have lots of other edges floating around. Yeah.
Se ele só tiver dois pontos conectados, ele não tem um emparelhamento perfeito.
Sorry, if what? So if there's only a single edge.
O que contém um emparelhamento perfeito? Porque se ele só tem uma linha, ele tem um emparelhamento perfeito.
So what I mean is you have to find something like this inside GMP.
Com todos os versos de...
Yeah, every single vertex must have degree 1. So a subgraph of GMP in which every vertex has degree exactly 1. So what's an obvious necessary condition?
And even
Sorry? Yeah. Very good. There we go. The minimum degree of GMP better be at least 1. What is the threshold for the minimum degree of G to be at least 1? How large does P have to be? How would you try and figure it out? So question. So for which functions, this is even vaguer, I'm just saying,
With high probability.
yeah, it's always with high probability or positive probability or probability at least a half or something, right? It's a vague version of the question. Let's see what we can prove.
P is much larger than 1 over 10 minus 1.
Right. So P. So what's the I? What's the approach that suggests that?
You pick each vertex and see the expected
Right.
number of equals.
Yeah. So you're implicitly defining for each vertex U a random variable U, which is the size of the neighborhood. So the degree. Okay. So what is the expected value of the degree? Yes, the degree in GNP, I guess. Degree in GNP of U. No, number of neighbors. What's the expectation of XU? Just what you said. Right?
Can you elaborate that a little more, please?
Sorry?
Can you elaborate that a little bit more, please?
This is the sum of all other vertices. V is not equal to U of the probability that UV is an edge of GMP. Right? So by linearity of expectation, so this is the sum of the indicator functions V in V of whatever, and V not equal to U of the indicator function that UV is an edge of GMP. Right? Just by linearity of expectation is this. This probability is just P always with n minus 1 of the vertices. Okay, so what does this prove?
There might be a problem because we just should have only one vertex will have an edge with high probability if P is much larger than 1 over n minus 1. If we
So-
try to account for every vertex,
Right. So yeah, you're seeing the problem ahead. There's already a problem. We haven't even proved that this one vertex has one. We've shown the threshold at which each vertex is likely to have a neighbor. Right? If P is smaller than 1 over n, a vertex is unlikely to have any neighbors. So most vertices will have no neighbors. Above 1 over n, each vertex itself is likely to have neighbors. Okay, we haven't proved it, but it's true. But we'd want every vertex to have a neighbor. So we're going to need the expected number to be quite a lot bigger than 1. Right? If the expected number is 5, your chance of failing is still reasonable, right? It's still constant. So what's a better way to... What's a better random variable to look at? So this turns out to be the wrong random variable to look at. What's a better one? So what are we trying to show? We're trying to show every vertex has at least one neighbor. What we're interested in knowing if every vertex has a neighbor. So what are we interested in counting? We want X to encode the answer to the question we're asking. Right? Exactly. The number of isolated vertices. Right? Right? That's what we want to know. We want to know if that number is 0 or not. Right? So in picking a random variable, you can always try and think, okay, this random variable, it should tell me the answer to my question. Right? So we care whether x is 0 or non-zero. Okay, so what's the expectation of x? So a way of remembering this, if you're a bit confused by this linearity of expectation stuff, so our random variables will always be of the form the number of somethings with some property. And the expectation is always the sum over the somethings of the probability they have the property. Right? The sum over, in this case, vertices of the probability that V has the property. Does that make sense? Right? We're always doing the number of somethings. The expectation is always the sum over somethings of the probability, somethings with a certain property, sum over things, probability, property. Right. Okay, so what's the probability that V is isolated? Exactly. So this is n times 1 minus p to the power n minus 1. And that is roughly what? Or at least it's at most what? Yeah, we should always use 1 minus p as at most e to the minus p. So n times e to the minus p times n minus 1. Note the expectation appeared here. It's not by chance. Which is less than 1 if so I want an exact, I would like to know exactly. Right? How do you solve this? Yeah, exactly. So this thing should be strictly bigger than log n. Right? E to the minus log n is 1 over n. So this should be bigger than log n over n minus 1. Right? Fact. E to the log n equals n. It's a deep fact from that you may remember from your early education. Okay. So if p is bigger than about log n over n, then there's some chance that we have no isolated vertex, right? Okay. So let's now turn this into a proof of something. So what do we want? What we want is, so this is if and only if, right? This last step. What do we want, though? We want to show that, so having no isolated vertices is not going to be enough. So we actually want, for the first part, to show that if p is smaller than something, you probably do have an isolated vertex. Okay? So let's try to prove some version of that. So proposition, if p is less than 1 minus epsilon times log n over n, then the probability that there exists an isolated vertex tends to 1. Okay. So there exists an isolated vertex with high probability. How are you going to prove that? So what do you know? When P is roughly this size, what do you know from this calculation? Yeah, I mean this is monotone. So roughly how large is expectation? So equals n times 1 minus p to the n minus 1. Which is at least, so okay, we should be a little bit careful because we have the inequality the other way around. But p is small, so I don't know what you prefer. So if you're happy with it, then I can just say, look, these things are basically the same if x is small. If you're not happy with it and you want to be precise, then we can say, all right, e to the minus x is actually 1 minus x plus big O x squared. Or we can say that 1 minus x is, so it's at most e to the minus x, and it's at least e to the minus x squared. Right, whichever you prefer. But there's basically an x squared, so here a p squared error in the exponent or wherever. P squared is like 1 over n squared. It doesn't matter. Okay, so I think I'm just going to write this with the understanding that the error is super, super tiny, right? But that's the order of the error. So sometimes the error really matters. So once you check it, you should be aware of how large it is. But here it's really small. So this is basically at least approximately n times e to the minus p times n is like 1 minus epsilon log n. Right? And there's an error of the form p squared times n, which is like big O log n squared over n. Okay? No, because there was an n here. Yeah, sorry, an n. Yeah. Here. Sorry, that n. Yeah. Okay? So right, so there's, yeah, so actually, now it's correct with some error term. Right. Should I put minus? I mean, this isn't, well, whatever. I mean, it doesn't matter. Right? Okay. So, trivial analysis tells you that what this is at least, let's ignore this one. This is n to the minus 1 minus epsilon. So this is n to the epsilon. I mean, over 2 if you like. Right? This is much smaller than 1. So the expected number of isolated vertices is big. It's like n to the epsilon. Does that imply that it's at least 1 with high probability? No. What you have to use? Chebyshev, right? So we have to bound the expected value of x squared. How do you bound the expected value of x squared? So x is the sum over vertices, the event that is isolated. So x squared, you have to worry about pairs of things, right? Pairs of vertices. What's the probability that they're both isolated? So this equals sum over uv probability u v are both isolated. Right. So what's the probability? Yeah, so you're going to have n minus 2 non-edges, n minus 2 more non-edges, and that one's got to be non-edge. So it's 2n minus 3. And that's true if u is not equal to v. Otherwise, it's what we had before. So it is n times n minus 1 times 1 minus p to the 2n minus 3 plus n times 1 minus p to the n minus 1. Right?
Is that divided by 2 and n minus 1 over 2?
No, because I want them to be ordered pairs. So I want it to be I want it to be very close to this squared. Remember, the variance is going to be this minus this squared. And so it's going to take away the main term and just leave us with an error term. Right? So it's equal to, this is almost equal to this thing squared, except not quite, because this will be 2n minus 2, this is 2n minus 3, that'll be n squared, and this is n times n minus 1. But the second order terms are smaller, right? I mean, it's sort of obvious, or should be sort of obvious, that probability u is isolated, the probability v is isolated, are almost independent. Right? They mostly just depend on these guys, and there's a little bit of correlation because they both use this non-edge. But it's very unlikely this is an edge, because p is very small, so the correlation between them is very weak. That's encoded in this calculation. Should I finish it? Should probably finish it, I guess. So let's go up here. This is equal to the expected value of x squared times n minus 1 over n times 1 minus p plus the expected value of x. Is that right? So the variance of x, so it's the expected value of x squared minus expected value of x squared, is do I mean 1 over this?
Yes.
I hope I do. Yeah. Thank you. Right. This is basically, so this is like 1 plus p, right? It's at most 1 plus 2p. Okay, and that's a bit less, that's less than 1, so we can ignore it. So it's at most, let's say 2p times the expected value of x squared. So x squared, if you will, actually, it's way better. Plus the expected value of x. And this is much, much smaller than the expected value of x squared. Why? So why is this true? So first, is it okay that this is true? Aha. So I took this thing and I subtracted off this. Right? So this is just here. So it's just this term you have to worry about. It's less than or equal to. This is less than 1. So that's fine. So it's just this term I have to worry about. And I claim that 1 minus p is at 1 over 1 minus p is at most 1 plus 2p. That's it. So the one gets cancelled by this guy. Okay. That's that step. So why is this step true? We're using two facts. Well, the first one should be obvious. This term is smaller than this because p is small. Right? P is much smaller than 1. I mean, in fact, it's like log n over n. And why is this much smaller than this?
It's square, right? Almost.
Yeah, because the expected value is big. Right? Right? We proved it here. So the variance is much smaller than expected value squared. So by Chebyshev, x is concentrated, but the expected value of x is large. So x is concentrated around something large. So with high probability, it's positive. Right? In fact, with high probability, it's close to n to the epsilon. Right? So there are many isolated vertices. Is it okay? Should I do that carefully, or are you happy? Who would like me to do that calculation carefully? Yeah? Okay. So I will, maybe over here. So the probability that x is at least 1 is at least the probability that x is at least the expected value over 2. Right? Just because the expected value is big. Which by Chebyshev is at least 1 minus the variance of x over the expected value squared times 4. So this is expected value of x is at least 2, and this is Chebyshev. Applied with t equal to this guy. And this thing tends to 1 when n tends to infinity, because the variance is much smaller than the expected value squared, which is exactly what we proved over here. Right? The variance of x is much smaller than the expected value squared. But that's what this means, sorry. It means variance divided by this tends to 0. That's exactly this statement. So exactly saying that this thing tends to 0, so this thing, this right-hand side tends to 1. So this thing tends to 1. It's okay? Okay. Right. So we proved this. Okay. So let's prove that this is the correct threshold. So, theorem. Probability that exists an isolated vertex. Probability that exists in a perfect matching in GMP tends to 0 or 1 if p is less than 1 minus epsilon log n over n. Okay, that's what we just proved. This means 1 if p is greater than 1 plus epsilon log n over n. proof. P is less than 1 minus epsilon log n over n implies, by Chebyshev, min degree of GMP is 0 with high probability. So what if P is greater than 1 plus epsilon times log n over n?
You're getting a result much sharper than the ones before, right?
Yes.
Before we were requiring that P over n will go to infinity or something.
Yeah. So I'll discuss this in some length later. But yeah, this. So previously we proved a threshold, that a certain property had a threshold. This is called a sharp threshold. Right? Yeah. So exactly the right word. But so if the probability goes from 0 to 1, or meaning like close to 0 to close to 1, when you multiply by 1 plus epsilon, that's called a sharp threshold. Yeah. Now, so I'll discuss afterwards exactly when that happens. Okay, so how are you going to show that there exists a perfect matching in GMP? Yeah, right. I mean, so as Baylor said in his class yesterday, like, if you want to find a matching, there's an obvious thing to use. Right? This is a very obvious and useful tool, right, that you should really engrave this in your memory. So it's extremely useful. I mean, extremely simple as well. So let's try to use Hall. So first things first. Hall's theorem is about bipartite graphs, and GMP is not bipartite. So what do you want to do? So I guess I should say 2NP, shouldn't I? Let me say 2NP. Oh, but then I have to put over 2n. Okay. I don't know what's easier. N is even. Yeah, maybe it's nicer. Yeah, I mean, I don't have to put log 2n, right? Okay, let's pretend n is even. So what are we going to do? So the trouble is at this stage, at this range of p, GNP. I mean, okay, you can take a bipartite subgraph. Yeah. So I think it's equivalent to what you just said. Is let's just partition the vertices into two parts arbitrarily, and just worry about edges between the two parts. Right. So let's just choose a partition. AB, so before we even start with A equal to B. Right, let's just partition them into two parts, and just only look at edges between. Right, so it seems like it's very expensive. It's throwing away half of the edges. Which seems bad, because if you're throwing away half the edges, aren't you changing the density by a factor of 2? And this is a sharp result. So we'll see that that's not actually a problem. But perhaps you can think for yourselves why it's not actually a problem. Am I cheating? No, I don't think I'm cheating. No, but sorry, it is a problem. Yeah, sorry. I'm being silly. Yeah, so I don't normally prove this in class, but I thought it would be fun to do it because we're doing Hall. So no, sorry, we have to be a bit more clever. This is not going to work. Okay, good. Let's try and be a bit more clever. Yeah, if we do that, we've thrown away half the edges and we're dead. So, what can we do? So we're worried about these vertices with degree 0. It's actually it's not quite as easy as I thought. What's a nice way to? I can't see that. So it's very clear that we can hammer this out, but it's nice to find a nice way of doing this. What's a nice way of finding this matching?
Check how many of them satisfies the property, and we have more than 2 to the k minus 1, and 2 to the n minus 1, then we're good.
Sorry.
Check how many neighborhoods satisfy this the whole condition. And if we have more than 2 to the n minus 1 of them, then we can claim that we have a set of more than n over 2 vertices that satisfies the whole condition.
So if more than half of the subset satisfy the condition, but you want them to satisfy it on the other side, right? Yeah, this is exactly the problem. So the reason that what I said wouldn't work is exactly that. So there won't be any isolated vertices, but there will be vertices that only have neighbours in their own side. Right? Actually, at this point, most things have lots of neighbours, but they might all land in your own side. So to choose a bipartition such that we're going to choose bipartition such that Hall's condition is satisfied. We're going to show that there exists a bipartition such that Hall's condition is satisfied. Show there exists one such that the number of times it fails is 0. So perhaps a natural thing to do would be to count the number of, so take a random bipartition and count the number of times we fail. So instead of considering just one of them, let's consider all bipartitions. So let A union B, so AB be a subset of vertices of GMP, size n over 2, chosen randomly. Okay, and let's let X be the number of subsets of A such that the neighbourhood of S intersect A complement, so minus A, is less than the size of S. Is this going to work? I think it might work. Does it make sense? So I would like, and then we'll count the expectation of X. What's the expectation of X? Yeah.
A is also
A is random, yeah. A is the random thing. There's nothing else. Yeah. So no, sorry. So I'm taking expectation here. Good question. I'm taking expectation over the randomness of GMP, so randomness of all the edges, and the randomness of A. So I'm averaging over everything. Sorry? Yes, I'm choosing them independently. Yeah, exactly. Yeah. So this is chosen randomly, independently of GMP. So, so I'm making this up as I go along. So please do check. Don't just believe blindly what I'm saying, right? So it's more likely than usual I'm going to make a mistake here. So, yeah.
So why is checking Hall's condition for every subset not because you can calculate explicitly, right? What the probability is that the
For every subset of the vertices, but the neighborhood in the whole graph.
yeah.
Because that's not what the theorem says. It doesn't tell you there's a matching then. So it's only valid in a bipartite graph. Yeah. So we have to be working in a bipartite graph to apply it. Yeah, exactly. Yeah. So what's this? So we're going to sum over S. What's the random event? So sum over S in what? So no. Why? So this is a more complicated example. A is random, right? We don't want to sum over a random collection of things. So let's sum over everything. Let's sum over all subsets. Everything random has to go here. So the probability that, so S is in A, so for every set S, this is a random event, and this is a random event. And n of S minus A is less than S. That's another random event. Right? Okay, how are we going to estimate these probabilities? Let me go over here. Yeah, please.
You're generating A, but with what probability?
So I'm choosing a uniformly random subset of size n over 2. So you should think of it as being, for each element of the vertex set, I'm tossing a coin and putting it in left or right probability half. It's not quite that, because I want to make sure I end up with exactly n over 2 elements. Otherwise, I'm in trouble. So actually, no, yeah, I want to make sure, I want to make sure it's exactly n over 2. Yeah, because I need to, yeah. Okay, so it's slightly more complicated, but we should think of it as being, it's very close to the distribution where you just toss a coin independently for each one. Right. Right. Out of space. Let's go over here. Right. So we've got the set S. It's got some neighborhood. And then there's the rest of the world, which is most of it. I mean, okay, S might be big, but the most important case is going to be S is small. So S, all of these guys need to be picked in A, which is probability roughly 2 to the minus the size of S, right? Not exactly, but close. And then also, the neighborhood of S that's not in A, so A looks like this. Here's A. Here's the bit of the neighborhood that's not in S. That needs to be smaller than S. Right? So how are we going to bound these two probabilities? It's also going to... it's also going to fail. It's also going to fail. I need to deal with small sets separately. Because if S is... So to see this is going to fail, just consider the size of S is 1. That's going to be the most important case. So what's this probability when the size of S is 1, roughly? So roughly speaking, for this vertex U, it's probably got about how many neighbours? About 1 minus epsilon times log n neighbours. And the probability they're all in A is roughly 2 to the minus this. And 2 to the minus this, it's not e to the minus this, is it? That's even worse. Is much, much bigger than 1 over n. So the expected number of vertices, if you're summing over all S, so in particular we're summing this over S of size 1, this is going to be much, much bigger than n to the epsilon. I want it to be small. Yeah, so even considering all of them, we're in some trouble. Okay, so what I think I'm going to prove instead, this must be the correct threshold. So that we can prove. Huh. Interesting. Yeah, so okay, so this is going to follow from Hall. And then perhaps you can think about what to do in between. I think maybe you actually need a non-trivial extra idea, it looks like. Okay. So if P is bigger, then we just partition the vertex set into 2 parts, as we were hoping, and apply so we claim that this bipartite graph in between A and B satisfies Hall's condition with high probability. Right. So how are we going to prove this?
Sorry, with respect to what probability? Choosing the sets?
So no, now the only randomness is in GMP. So A and B are fixed. I'm going to fix them at the start.
For all graphs?
Yeah.
Okay.
Yeah. Yeah, fix them before looking at GMP. So at the start, everything's symmetric, so just any old way. Yeah, so to improve this 2 to a 1, we'd have to somehow use the fact that we have lots of choice in the bipartition. And yeah, doing it randomly, uniformly doesn't seem to work. We'd have to do something a bit cleverer, looking at the graph and then choosing the partition. Anyway, but this will be just straightforward. So what should we do? How are you going to prove that it satisfies the Hall's condition? So I already half told you. So or what do we always do? Yeah, which is, so tell me.
Count the number of
Uh-huh.
subsets
Uh-huh.
such that in the neighborhood is smaller.
Yeah. Good. Okay. And what's the expectation of x?
We need to sum in the subset A.
Yeah. Now not random. So that's okay. Of probability of this thing. Oh, intersect B is less than S. Right, so what's this probability? It's over here. Right, there's some kind of bound on this probability.
Can you like count every subset of B of size of S minus 1? And then the probability there are no edges outside that.
That sounds like a pretty good idea. Right. So to bound this probability, let's define a random variable y, which is the number of S minus 1 sets such that, call them W, such that the neighborhood of S is contained in W. Is this going to work?
Y should be 0.
I think it's not quite going to work. Yeah, we want y to be the expectation to be less than 1, or the expectation to be small. I think it's not going to work for S of size 2, say. Where is it? Oh, you win the end twice. You have to sum over. It's not quite going to be strong enough because we're not using. So when the neighborhood of something is size 1, say a set of size 1 has neighborhood size 1, then there's a probability that you miss everybody else, which is about e to the minus p times n, so 1 over n. There's also a probability p of having this edge. But then you have to sum over these vertices. So n vertices, but probability times p, so another p times n doesn't really matter. But if you're not using the fact that this edge is present, then you're going to lose that factor of p, and so you're in some trouble. So I'm going to be a bit more careful. It's quite a bit trickier than the. Yeah. I'm going to give you a homework problem, which is the thing I normally prove in class, which is quite a bit easier, but an easier version of this. So, sorry?
We have a bound for the minimum degree, right?
Yes.
This doesn't help you because, well, if we have a set S and you have a bound for the minimal degree, then
So
we will expect that you have n of S bigger.
So it deals with, right, but a bound of the minimum degree was not that great, right? It was 1. So it deals with the case S equals 1. I agree. Though we didn't even prove that, right? We proved that if P was smaller, then you did have, you had vertices of degree 0.
But now we have 2
So-
concepts also, right?
Yeah, right, which we need to show that this is true when S is 1 to make sure that you have enough neighbors. So maybe we want to do the sum over, so it depends on the size of S. So when S is size 1, you just need to have one neighbor. Right? And make sure you don't have any isolated vertices. So perhaps we'll, sort of a warm up for this. We'll have 10 minutes. Okay. So case 1, let's suppose that S equals 1. Then what are we trying to do? We're trying to prove that we're going to bound the probability that this vertex is isolated. Right? This is the probability that, so if S equals U, probability U is isolated, so degree of U is 0, sorry. So I'm saying, I'll just write it like this. Neighborhood of S equals B, intersection B is 0, is what? It's equal to
1 minus B to
the
the n over 2.
n over 2, exactly, which is at most e to the minus Pn over 2, which by this is at most e to the minus 2 plus epsilon over 2 log n, which tends to 0. Sorry, better than that, which is equal to, let's say, n to the minus 1 plus epsilon over 2. Yeah, so it's important this is smaller than 1 over n. Right? We're going to sum over S. So this is good enough. So summing over sets of size 1 of this probability is at most n to the minus epsilon over 2, which goes to 0. Okay, so sets of size 1 are OK. What about sets of size 2? Let's see if we can do something in general. Right. So we're going to try and make a bit more space. So this equals 2. Equals what? So it could be that the intersection is that neither of them sends any edges. 1 minus p to the 2n, sorry, 2n over 2, n. Right, so these two vertices, where are they? Here they are. S, 2 vertices. This sends, this is now size 1 or 0. So it could be they both send none. It could be one of them sends none, the other one sends 1. This one sends none, this one sends 1, or they both send 1 to the same one. So I guess we have to write down all of the possibilities. Yeah, so what am I saying? So in this case, there's 2 vertices in S, and at most 1 vertex over here, and at most 2 edges. So this is probably actually the most likely thing. Then we also have to add over, there's n choices for this vertex. There's neither sends any edges to anybody else, n minus 2. Right. And then the other two could be edges or non-edges. But at least one of them is an edge. Times 2. Okay, maybe I'll say 2p plus p squared. Yeah, so maybe if I'm doing equals, aren't I? So really I mean twice p, 1 minus p, plus p squared. Okay, now it's really equals. Okay, so they can be edge, non-edge, non-edge, edge, or edge, edge. Right. So now what? The main term is this 2p times 1, right? So this is approximately, as I say at most, e to the minus p times n. This is plus, let's say, so the 2p minus p squared beats this one. So it's at most 2pn 1 minus p to the n minus 2. Which I should write as e to the minus p n minus 2. Now this thing, let's just recall that by this, e to the minus p times n is at most, by our assumption on p, n to the minus 2 minus epsilon. Right? This is at most n to the minus 2 minus epsilon. This is basically the same thing, but now we've got a p times n, so we have to multiply by log n. Plus 2, whatever, 4 log n, 5 log n, times n to the minus 2 minus epsilon. And this e to the minus 2p doesn't matter. It's almost 1. It's absorbed here. Right? So now sum this over all sets of size 2, multiply by n squared, and it's again small. Okay, so now we have to do it in general. This looks a bit complicated, but okay, not crazily complicated. So let's try and do it in general. Maybe I'll make some more space. This thing is at most. Let's put these things down here. So S, possible neighborhood of S. So we should sum over all W in B. Size of W is less than the size of S. So we are doing this, but it should be the probability this is exactly the right set. So it's equal to the neighborhood. So what do we get? Outside, so we get 1 minus p to the S times n over 2 minus size of W. Times, okay, so we need to have all the different possibilities you could have here, but every vertex has to get hit. So there must be at least one edge from each. So it's at least p to the W, right? Because you need to have at least one edge coming out of each. Okay, but we should multiply by the number of choices for this graph, I guess. So for these edges, which is basically S times W, choose W. And it's not quite that because I'm also assuming that all the rest are non-edges. But I'm not using the 1 minus p for the rest of them, so I think it actually includes it. So I think actually this is a suitable upper bound. This is the expected number of sets of W edges that hit in between S and W. You know you need at least W edges, and they can be in this many positions. So perhaps I'll perhaps an exercise to check this is really correct. So I've subtly sort of sneakily used Markov here without telling you. Okay? Or use the union bound, perhaps, if you like. Okay, so now this is at most what? Right, so I want to sum over these W. So it's only the size of W that matters. So let's suppose that the size of S is K. So let's sum over L is 0 to K minus 1, size of W. This is at most e to the minus K times n over 2 minus L times p to the L. And this thing is at most e times K to the L. I now claim that this is decreasing in L. When you increase L by 1, you multiply by e to the K times K times P. It's only true if, it's true if K is, if K is smaller than log n, then it's decreasing in P, otherwise it's not. Because the neighborhood is typically going to be of size, what? Log n. What happens if K is very large? Okay, I'm suddenly worried I have to deal with cases. That wouldn't be so nice. But at least when K is small, then we can check this goes to 0. Because e to the minus K times n over 2, there's a P here, P. Okay, that's better. Right? 1 minus P, e to the minus P. That's important. Good. And so as long as K is smaller than 1 over P, then this is decreasing in L. So I'd like to take L to be basically K minus 1. And if I do so, e to the minus P times n is this guy. So this thing becomes like n to the minus 2 plus epsilon times K over 2. And this is P times K. This is small. And I didn't count. Sorry. I forgot to count the number of choices for W. So I should multiply all of this by n over 2, choose L. Yes. Sorry about that. So now what we basically have is n to the minus 2 plus epsilon K over 2. And then all of this stuff is basically P times K times n over L to the L. And K is bigger than L. But so I claim if L is K, this is giving you like log n to the K, and this is giving you, should be worse than that. No, it's not that bad. Maybe it's okay. Are we winning by that much? Yeah, I think we're really winning by a lot. It's too much. We're winning by too much. What have I done wrong? Yeah?
Why did you include L in, so you're estimating e to the minus pk, all that?
Yeah.
By n minus 2. Doesn't that have to be an L somewhere in there?
Sorry? This is having non-edges from S to the rest of B, the bar outside W.
I was just thinking of the e to that term.
Yeah.
Minus pk,
Which is this guy.
the one below.
Yeah, it's the same thing. This is bounding that.
Yeah, but does that correspond to the n to the minus 2?
Yeah, sorry, yeah, exactly.
And then where did the L go?
Oh, I ignored it because I'm thinking of L being small. Sorry. Yeah, so when L is very large, then perhaps we must do something a little bit different. Yeah, but let's assume that L is much smaller than N. Yeah, sorry. Yeah, let's assume that k is much smaller than n. I think the other case you have to do slightly differently. So it should be easier than the case, but we do get this, right? N to the minus this thing by that. And then that's fighting with this, right? And should beat it. But then this p is just extra. Why is the p extra? Ah! I should sum over s as well. That's why. Sorry. So what I really want to do, this is for a particular s. So what we really have to beat is n choose k. And we do beat it because we get basically n to the minus k here. Right? So this thing really is extra. And it's only the epsilon that has to beat this bit. And it does because this is basically log n to the k. So, so I try to write that out slightly more fully. I'm not sure. So this thing, what we're really doing here, yeah. So we're come to the expected number of copies of S in A. So this thing, all of this thing, is at most so sum over k, which is the size of S, sum over choices for S, right, times sum over the size of the neighborhood of S, that's less than k, sum over choices for the neighborhood, right, times the probability that it's the neighborhood. Right? The probability that this W. So we've summed over sets S and sets W, that W is the neighborhood of S. Is it okay? No? Completely not. Is it okay for anybody? No, 0 people. So this is choosing S. So this is choices for S. Hello? Hello. Sorry. Okay. 1 minute. Of the probability that this is exactly the neighborhood, which is supposed to be counted by this. And the claim is this goes to 0 because this e to the minus pk n over 2 minus l beats the other things. Right? This is k times l choose l. Goes to 0. Okay. Right, sorry. So we let the other people in. Homework problem.